So, continuity and locality. There's one I disagreed with that you...
Good.
So I can't remember what it was now.
Oh.
It down.
It's good to disagree.
I have to come back to it. Yeah, I can't remember what it was now. Anyway, so these individually existing entities like particles follow continuous trajectories in space-time, or that the value of field at any given spatial location changes continuously as we do this time evolution. And then, traditionally, you assume locality as well, that at a given instance, that if you have on your spatial structure two separate individually existing entities which are spatially separated, then they can have no influence on each other. You don't have instantaneous action at a distance. And what's more, what has always been there in the background, although quantum theory and relativity both challenge this, or they certainly challenge locality in that sense, but that if we're going to define these basic entities that are individually existing, then the properties that define them are also local. So you don't really admit individually existing entities that are somehow non-local within this space. Wants to come back. He's just going to rotate the thing.
Not too much, George.
Too much.
George is distorted now.
Oh, we get another
hang on.
perspective.
Yeah,
that's right.
Oh,
So
that's
No.
okay, yeah. Is that good like that? Sorry. Yes.
So we know that quantum theory messes up this idea of interactions being local if we try to define these individually existing entities. So if we do just the EPR type experiment, then we know that locality, or this notion of locality is messed up. But general relativity also gives us problems with this idea of space-time in this way. So firstly, as I've said, in general relativity, we know that the properties of the space-time structure and the matter, the individually existing entities, are interdependent. They're not two separate things anymore. But you're still assuming locality and continuity as basic. However, you start to get, these are not really, it's not really a challenge on this idea that the properties defining individually existing entities have to be local, but certainly things which seem to make sense for the system become to, things like the gravitational energy of a system are essentially global or non-local, even within general relativity. So, although this doesn't immediately challenge my assumption that the defining properties of entities have to be local, if we go beyond a single particle, then we start to get these global notions like the gravitational energy of the system, which start to challenge the idea that everything we can sensibly define has got to be locally defined. And then, of course, we all know that the famous singularity theorems from Stephen Hawking and Roger Penrose reveal that if you actually have matter-containing solutions to the equations of general relativity, then there must be some singularity somewhere where the space-time, the basic idea of the space-time manifold falls apart as you get singularities. Not necessarily a problem in its own right, but it is because when we want to bring in quantum theory, we need to care about what happens at these points. Quantum mechanics we're all familiar with. We're still assuming a continuous a priori space-time background in there on which we describe the evolution of space and as time. We know there's non-locality and non-separability. It's exemplified very nicely by the EPR experiment. And that we also know that relativistic field theories of any description really that people have tried to make exhibit these divergences, which can be renormalized in most cases, but once again they call into the question really of whether this idea of putting on a continuous space-time structure at the outset is the right way to go about this.
Because in GR you can't do that. You can't renormalize.
Right. I mean, when you can, I mean, you can still argue that we haven't found renormalizable. Yeah, I mean, these are all old arguments, which are really just motivating the kind of process approach. So we know all of these things. Sorry, this is kind of, I know a lot of these things are a bit trivial for this audience.
No, not for all the audience.
Okay. Maybe some of the mathematicians.
Freddie, for example.
For me, it's not trivial.
Even
Alright,
Freddie.
sorry, I'm I think you're not doing this audience. Sorry.
That's a sacrifice again.
It's not trivial for me anymore.
You know the golden rule, always stop at the most stupid question of the day.
So as a bold general statement, I think it's fair to say that in their current formalism, quantum mechanics and general relativity are mutually incompatible in their mathematical formulations. And but specifically things like the Hawking-Penrose singularity theorem telling us that we have to get at least one singularity somewhere in a universe containing matter, tell us that although we might argue that we can pretty much ignore situations where we need quantum theory and general relativity together, we can argue that maybe this is just true statistically on a large enough scale. At these points, these singularities which must occur, then we really do need to take into account the quantum effects and the general relativistic effects simultaneously. So it's not something we can, even if we take the position of being technologists and saying, well, we don't really care about the philosophy of what's underlying our equations, we can't even take that viewpoint saying, I'm just a technologist, I just want things that can actually predict outcomes, because we're going to have problems in particular situations that will occur. So this is a reason why we have to try to do quantum gravity. It's not an option, really. It's not a luxury. And it could actually bring us benefits. I mean, we could hope that all this effort of trying to make quantum gravity would actually bring us benefit in, if we had this theory, that the divergences would have disappeared, maybe the singularities will disappear if we have a proper quantum theory, and various aspects of quantum theory which are somewhat problematical. So the state vector reduction, the collapse of the wave function, whatever you want to call it, may even disappear. That gravity may help us to explain why wave functions collapse. So I remembered what it was that I didn't agree with you with. You said that you had continuity and locality and various things like that, and that quantum mechanics broke locality and gave you non-locality. And you said it also gave you this, I can't remember what words you used, but you were talking about collapse. Because you said it gave you indeterminism, and it gave you...
No,
that's only in collapse, and you were talking about Schrödinger evolution in what you were doing in the maths. So Schrödinger evolution does not give you state vector reduction. So all the maths we're talking about, all the maths we've talked about so far, is only Schrödinger evolution, which is only half of quantum mechanics.
Yeah.
You've got this half of quantum mechanics which just gives you unitary evolution on Hilbert's space, and then you do state vector reduction as basically an ad hoc algorithm that's been introduced. And so there's not just a problem here that we have to somehow put quantum mechanics and gravity together. We already have a big problem with quantum mechanics. That we have a great mathematical description. We may not understand why the mathematical description is as it is, but we certainly have a good handle on the mathematical description of unitary Schrödinger evolution in quantum theory. And then we have to stick on this state vector reduction to make things happen. And so that's, even without general relativity, that's a good reason why we have to try to find some way into this and find out why that is happening. So those are the motivations for wanting to do this, and over the years there have been many, many famous attempts to try to bring quantum theory and gravitation together. It is not my intention to give a thorough review of any of them at all. I think on the next slide or one after I'll give a quick list of some of the approaches